Now, so what is the objective of tensile test? It is to compare the tensile strength of the metallic metals, to compare yield point of these metals, to compare the ductility, that is percentage elongation, percentage reduction in area, to compare their necking phenomenon, to compare their modular elasticity, draw, analyze, and compare their strength and stress strain curve. The tensile strength of mild steel of prime importance to an engineer because it is used in many ways civil structures like bridges or railways, industrial bridge, water tank, transmission towers, etc. Mild steel is subjected to direct tension due to bending in some of the components used in aforesaid structure. Determination of the shape and size of this component requires the knowledge of capacity to deform consistent with the specification of strength, safety, and reliability. These are obtained from stress strain curve of the machine. Metallic static strength is important in two ways. Resistance to permanent deformation. This kind of strength relates to prevent bending, twisting, or denting of a metal permanently. On the other hand, the yield point stress must be reached or exceeded during the manufacturing of metal products. They are made by forming or work in methods such as rolling, drawing. Thus, yield point is a stress level which should not be exceeded in service, must be exceeded in manufacturing by forming. So, there are 2 points. One is elastic limit, another is yield point. For this, items which are used in structure, which should not be no way permanently deformed, that should be loaded up to the elastic limit, which can be restored after releasing the load. And for the case of a manufacturing items, we have to say by drawing, by rolling or other items, we have to load the component up to the last yield point, and it remains so that this deformation exists and remains there as per your product itself. And so the yield point should not be exceeded in service and must be exceeded in the manufacturing by forming. The ultimate tensile stress, if the strength is capable of exerting against being fractured, that is broken in surface. When a stress equal to the ultimate strength, tensile strength is therefore a limiting stress level which must not be exceeded either in manufacturing or in service. What is ultimate? Ultimate tensile stress. Ultimate is the maximum. Maximum stress a material can exert up to, which it will, because it will break it up to, which will break or fractured in service. So it should not be loaded up to that loaded, because it will then tear and break the whole structure. That is the limiting stress which must not be no way exceeded after manufacturing and service. Now, both yield point and ultimate stresses are among the most important characters of the material measured by the tensile test. Next comes the ductility, the property which a material must possess to some extent degree at least in order to be formed into different shapes by rolling, by stretching, by bending, by drawing, hammering, or other non-cutting and non-metallic methods. For cutting the metal in lathe or other machine tools into different shape, it is not covering this type of phenomenon. This phenomenon is covered by forming the metal in different shape like stretching, bending, drawing, hammering or forging into other non-cutting but non-metallic method. Ductility therefore is very extremely useful when for necessary property. And the tensile stress provided two methods of measuring the specific degree of ductility, which is a material possession. One of these measures ductility in terms of percentage elongation specimen, and other in terms of percentage reduction in its area of cross section. So we have to take the measure of how much percentage of its length is increased, and at the same time how much percentage of its diameter is reducing. Percentage measure of length by stretching of the tension specimen up to the time of fracture. It expresses the increase in length of a measured portion of the specimen as percentage of the original length height. Therefore, reduction in cross-sectional area is a measurement of the cross-section as the tensile specimen is stretched. It expresses the decrease in cross-sectional area as a percentage of the original cross-section. So cross-sectional area, reduction in cross-sectional area due to the increase, it represents the decrease in cross-sectional area as a percentage of original cross-section. Elasticity. A portion property by value of which a metal returns to the original dimension after the removal of stress. It is usual characteristic of the design of springs or any other object. Shows elastic deformation must be controlled. A metal's elasticity is commonly expressed in terms of modulus elasticity. It is the ratio of stress to strain within the exclusive elastic deformation range of the material's performance, determined by the data obtained in a loop tensile test. Greater the modulus rigidity of the metal, stiffer or more rigid the material. That is, more stress is required to deform it by a fixed amount. So, material elasticity is that amount is a phenomenon which tells us the material returns to the original position before the external load is removed. Now, every material should have certain strength to show elasticity up to a certain length. And stronger the material, more that is more elastic, and higher will be their modulus of rigidity and modulus of elasticity. Next, stress strain diagram. As a part of precise stress support, it is often necessary to draw a stress strain diagram. With the performance of the tested material by graphically express the stress during the performance as a stress section of the strain and developed by the pulling action of the testing method, which from the start of the pulling to the occurrence of fracture. This shape of the cross-section diagram indicates the general characteristic of the stress strain diagram, tested material as well as its specific engineering properties. To draw the complete stress strain diagram, suitable stress strain scale should be stretched to make the entire curve within the proper limit. So apparatus are supposed to be used: universal testing machine, micrometer, a vernier calipers, and extensometer and divider, and specimens. The load should be proper for this column. Extensometer reading is to be proper for this column. Stress induced as given by the extensometer is given here, and strain induced act given by the extensometer will also given here. So process. First of all, you have to mark the gauge length as per spec and record it accurately. Gauge length is the length between the two dumbbell shape, but the straight shape portion of your test piece or workpiece or test specimen. This is the gauge length, and other the dumbbell or thicker portion of thicker diameter is used for gripping the metal in the testing machine. Gauge length should be the length between these two dumbbell, but should be excluded the length of the dumbbell. Grip the specimen vertically and firmly on the jaw of the universal testing machine and adjust the machine to read the zero. First, you have to grip it the jaw. How? We'll we'll open the rack by rotating the front handle for both top plate as well as intermediate plate. Place the rod in proper position over this hole, and then again rotate in the clockwise direction, anti-clockwise direction to close the rack to the dumbbell shaped end of the workpiece. Then you rotate and fix the nut in front of this double shape item, in front of the rack, kept in front of the rack, which helps us to ensure the grip is perfectly. Now, next increase the load gradually up to 150. We don't have any particular shape or chart giving the sudden rise in load. What you have to do by your own experience, by adjusting the loading knob slowly but accurately, so that by looking at the unit of the machine, we can know how much load is to be required. Your machine is required to break. Now, the loading should be continued till the end point is reached. Then It indicated the extension meter showing values of extension, recorded the load at the yield point. At the point of tool, remove the extension and perform the braking. Continue the brake with the help of uh, the bringer of the machine or the VSD driver. Record the extension and deferred extension and deferred load at the levels of 50 kg. Note and record the maximum load attained and breaking load. Remove the broken pieces and note and record the type of fracture. Fit the pieces together, measure the final length of the gauge, and record F, LF was measuring the final length between the gauge length and the record, and show the measurement of final diameter of the bar. Remove the bolting pieces, note and record the type of fracture. Calculate the yield point and elongation, percent reduction. Draw the statement graph of my steel, indicate your point, elastic and plastic, ultimately, and electric value. That repeat the procedure 2 to 12 for every session, unless our copper is registered by the binding. The observation: first, sketch the final specimen, sketch the shape, sketch the specimen and complete failure, plot the stress curve, make the various characteristic points, determine the yield strength and breaking ultimate length of the metal from the above curve. Determine the modular viscosity, determine the percentage elongation of the material. Result, put all the result here. Precaution, apply the load and uniform lead, remove the extension meter underneath the loader has to be reached. Do not use extension meter when using cast causes on either the metal, but care should be taken to remove before the specimen fractures. Next, compression test. To perform the compression test, we have to follow the following theory. There are several materials in engineering practice that are mainly used for construct compressive load. Say concrete, brick, wood. They are commonly used for compression, but not for tension. Therefore, mechanical properties of the materials are often evaluated. Therefore, various in tension and compression are similar to, but they are different in test diagram or more features, particularly the design materials, which is now understanding. For compression test, cylinder specimen of above standard size of to diameter rods are compressed between two plates. The mechanical properties such as yield strength, ultimate compressive strength, method of toughness, and as yield strength increases, can be determined for brick metals in common. For ductile metal, however, the ultimate compressive strength cannot be defined because ductile metal generally keeps on extending in lateral direction as compressive stress increases. This lateral expansion continues to take place, whereby an increase in ultimately the specimen must turn into this. This lateral bulging of ductile material apparent bulging of the method this their expansion continues to take place wherever increase and ultimately the extent must be turned into a disc. The lateral bulging of ductile material almost is to might enable it to resist almost indefinitely large forces without fracture. The specimen, platen specimen, sometimes be the space for universally arbitrarily chosen deformation. Often the ability to undergo Lateral plastic deformation under the compression is called, it often is called malleability of the ductile material, but its property cannot be defined as quantitatively. So, if we take a steel ball, steel rod of active length and compress it, it will not break, but it will provide in all four directions to make it in form of a drilled hole. And the ability to undergo compressive strength of ductile material, often the ability to use undergo large plastic deformation under compression is called ability to at atomic level, the modulus of elasticity and modulus of resistance for ductile material can be evaluated in compression as in tension, but modulus of toughness cannot be defined. At atomic level, unlike tensile stress, no specific maximum persistent stress is required. Thus, the compression will not become the cause of failure and always result in elastic stress. Polymetric metal like rubber, cork would show distinctly different behavior in tension compression. In tension, the coiled molecules are fast uncoiled in strength uh, and then started straining wherever transmitters are being shown. So, but stiffness follows by the high stiffness as well. On the other hand, compression may tend to cause further cooling of the initial state formed by elastic compression of molecules. It is like wood, cork, contain tubular shell structure. These shells are attached in tension but may buckle in compression. The buckling of tubular cells will result in intermediate decrease of thickness as the cells are completely compacted with increases compressive stress and the stiffness will further decrease. Now the compression of brittle material. For most brittle material, elastic properties of elastic limit, modulus resistance, yield strength, modulus rigidity, same in tension and compression. The ultimate compressive strength of the most brittle material is different that of ultimate tensile strength. For concrete, ultimate compressive strength is about 10 times higher than ultimate tensile strength. Compression is features due to the shearing along a plane inclined to the axis. The orientation of the plane of shear is affected by the presence of normal compressive stress, and the final structure does not even offer even along the length of the maximum shearing strength, but which is declared at an angle 45 degrees with the axis of the orientation of the plane of shear affects the presence of normal compressive stress, and final fracture does not often occur when along the stress of maximum shear stress, which is around angle of 45 degrees with the axis. The orientation of plane varies between 35 to 45 degrees with the x-axis. Even the brittle material, some lateral bulging will tend to occur. The lateral deformation gets restricted at flat specimen due to friction between the parts and the specimen. Friction reduces for longer specimen. If the compression specimen is too long, it must have a tendency to buckle. So compressive specimen has to be chosen very properly. The determination of the compressive strength is to between at the ratio. This is the ratio that 1.5 fractures bed plate may insert ends, which is undesirable. It may be noted that brittle material in which the atomic bonds are not re-established will probably ultimately fracture due to slip, which may occur along one or several planes. The latter failure is fragmentation. while cracks, pores, holes play very important roles in reducing tensile strength. Some does not become active under compressive stress. May further close and net compressive strength is higher than the tensile strength, particularly in case of brittle metal. Tensile and compressive stress is the material with the tensile strength, compressive strength, and ratio. Concrete tensile is almost 12% less. Uh, Plexiglass 72 to 1000 is 65, ammonia ceramic 9.5, and so. The compression is terminated if excessive deformation occurs and specimen does not fracture. Compression specimen, hydrostatic compression, in which every element is subjected to equal compression stresses in all three directions, a state of stress obtainable when a body is submerged in water does not cause any distortion but produces only volume reduction. In such a case, the specimen may not fall because at the atomic level, such state of stress will not push along. Most experimental important effect that arises in compression test is the application of load. The ability to load has to be determined from platen. Normal one contact with the moving process is made self-aligning with a special head to specimen. Because of the friction with the loading plate at top of the specimen, material immediately below the top surface is subjected to near hydrostatic stress and avoids failure. The compressive stress is direct perpendicular to the load axis because it is away from the loading surface. It does not vary before the at least diameter of the specimen. So the specimen length of 3D is normally accommodated. But the top surface is also recommended for to be smooth and friction-free. In some specimens, loose cuts, circular concentric groups are created to hold lubricant, especially specimens of ductile material. The problem of bulging a mineral is in concrete, and hence one I by L by D is into is often used for this material. Yet another method, the ends are made of conical hollow to receive similar loading. The angle of cones is equal to angle of friction between the metals of platen and specimen, and it is not readily known. It is important that the compression force must be applied so that the rate of straining is constant. Most material requires to be tested in compression are by viscoelastic in nature and not so much equilibrium readily. Prescribed strain rates are therefore mentioned. For any material having a stress straining form of figure 1, the stresses ultimate yield point, ultimate elastic limit, and ultimate limit. And they take this particular cup shape form here. And sigma ultimate F force divided by AS and sigma broken FB divided by A theta. This is strain hardening, there is necking, and this is the ultimate tensile stress and loading, reloading, ductility, and strain, stress and elastic limit. Let us go for that portion. Bending test. Now, here is aim to, of course, perform the bending test. UTM, bending fixture, vernier caliper, meter rod, and test piece. Bending test is performed on beam by using 3-point loading system. Bending fixture is supported on the platform of hydraulic cylinder of the UTM. Loading is held in the middle crosshead at a particular load. Deflection may occur at the center of the beam and determined by using a dial gauge. Deflection at this beam center is given by sigma WL to the power 3 divided by 48 EI. Procedure: first you have to measure length, width, and thickness of the test beam by vernier calipers. Place the bending fixture on the lower slot side of the testing machine. Place the test fixture on the roller of the bending fixture. By loading the dial gauge in the stand, take the specific handle of the test piece, start the machining and note the load and dial gauge reading. Plot the graph between dial load and reading. This count it should be noted. Length of the beam, width of the beam, thickness of the beam is known. So load in Newton, deflection in Newton, and Young's modulus in Newton can be done. Then what we know deflection, we know load, we know length, and so even Young's modulus can be calculated, and I is also known as per the diameter. So E can be calculated here, and I is given here P to the power 2 12 by 12. So E is only unknown factor which can be calculated here. And briefly narrating the procedure to run UTM machine, UTM digital device. Next, after opening the PC, we have to click on PM CRODS. It is shortcut. Username and password, generally UTM and password both are same. Then offline machine idle page come up. Click input, metals to select, company number, reference number, put anything, sample number, all given, sample height is given, trim length is all given, party code, sample, etc. Then fix the sample on the UTM machine, loading valve just open, release valve close. To accommodate the sample, intermediate stroke is to made up and down. Click on the up and down button as required. Reset load, click, reset peak, click on the peak arrow. Then click start. Rod is broken. A page will automatically come up. Put the final diameter of the rod after breaking. Put the final length and calculate. Check the select the yield icon. Select yield on the graph and look OK. Save OK and final parameter page. Report page comes up. Click. Then select the report page. Click report, load and displacement. Then number of test pieces, report, and then computed. Then go to the UTM report printing. This is the process. Next, let us go through few loadings.
Good morning everyone. So today we are going to do the tension test on mild steel rod. So for that we are using the universal testing machine, which is having a wide variety of applications in civil engineering. So here we have two compartments in universal testing machine. One is for the tensioning purpose and the other one is for the compression purpose. So in this compression straining compartment, we can do double shear test, bending test and rebending test. But here we are going to do the tensioning test. So here the other part of the machine is that it's a load indicator which is having two pointers. One is a dummy pointer and the other is a load pointer. And the universal testing machine has four load ranges, that is 0 to 60, 0 to 120, 0 to 300 and 0 to 600, which can be selected using the range selector. It has two valves, one is the release valve and the other one is the control valve, and there are some control buttons over here. Now coming to the experiment, first we are having the mild steel rod, our test specimen. Then we are having the punching tool, a chalk piece, and a vernier calipers to measure the diameter. Then the tape, measuring tape as well as the measuring scale. Now for taking the elongations to plot the stress strain graph, we are having the extensometer in our hand, which is having two dial gauges, each is having a least count of 0.01 mm. And the limbs are selected on the basis of gauge length. Here for convenience we are taking 10 cm limb. Now is a typical stress strain curve for the mild steel. The OA is the linear portion and whose slope will give us the modulus of elasticity. A is the proportionality limit, B is the elastic limit, C dash and C are respectively the upper yield point and the lower yield point. The portion CD is the yield plateau, D is the strain hardening region, and E is the ultimate stress and F is the breaking stress. Now to start with, first we have to measure the diameter of the mild steel using the vernier calipers. So the diameter is 12 mm. So from that we will get the area by using the formula pi by 4 d square, and we assume an approximate ultimate stress of 600 megapascal. By multiplying it with this ultimate stress, we will get the expected ultimate load. So usually our expected ultimate load falls in the range 0 to 120. So which can be selected using the range selector. Now behind this machine we have to put counterweights corresponding to this range. So here we are having A is equal to 60 kilonewton and A plus B equal to 120 kilonewton. So for the range 0 to 120 we have to put both this A and B. Before placing the rod in the machine, we have to mark the gauge length in this rod. So, gauge length is calculated using the formula L naught is equal to 5.65 root A naught. So, suppose we are getting 6 centimeter gauge length, then first we have to measure the total span of the rod, mark its midpoint. Now from the midpoint, on either side of the midpoint, we have to take half the gauge length. Now from this point onwards, we have to take the whole gauge length and mark it across, completely across the rod. Make sure that you put a 10 centimeter in excess here, because when we are fixing it should be convenient. We have to punch it using the punch tool. The point should be punched and then we have to keep it in the machine. So first we have to tighten the top crosset, which is the fixed crosset. This is the movable crosset, the middle crosset, which can be adjusted using these blue buttons. Now we can, after placing the rod, we can now fix the extensometer. The elongation readings are taken for 2 kilonewton interval. After taking the sufficient readings, we have to remove the extensometer. Now we can switch on the machine. Now we have to gradually release the control valve. specimen out from the machine and observe the neck to be a cup and cone in shape. Now find out the neck diameter using the vernier calipers. We'll get the load corresponding to the extensometer reading, and the actual extensometer can be found out by multiplying the divisions into least count. Now coming to the stress can be obtained by force by area and strain is delta L by LE, where LE is the extensometer, that limb length or the gauge length. That here we are taking it as 10 centimeter. Now from that we can plot a straight line graph whose slope will give us the modulus of elasticity. Now we can find the actual breaking stress as well as the nominal breaking stress by dividing the breaking load by the actual area that we already found out earlier, and by finding out the neck area we can find out the actual breaking stress. Now the percentage elongation can be found out by measuring the final gauge length, and the final gauge length minus initial gauge length by the initial gauge length expressed in percentage will give you the percentage in elongation. Now we can conclude our experiment. These are the procedures to be followed. First, clean the given rod with a sandpaper, measure the diameter of the rod at 3 different points and calculate the mean diameter. Calculate the gauge length using the formula 5.65 root A naught and mark the entire length of the rod at this gauge length. Adjust the range selector knob to the range selected for the test. Interpose the test specimen between the chucks of upper crosshead and clamp it tightly with the handle. Lift the lower crosshead to the required position to grip the test piece with the crosshead adjusting knob. Turn the handle to clamp the test specimen to the lower crosshead. Adjust the load pointer and the dummy pointer of the machine to 0 of the dial gauge. The specimen is subjected to tensile load by turning the load control knob rightwards. At some point, the load pointer becomes stationary for a while. The load corresponding to this point is noted as the yield point load. Increase the load further until it reaches a maximum value, which is the ultimate load capacity. After that, the load pointer comes back leaving the dummy at the ultimate load and the specimen breaks at a load lower than the ultimate load. The position of the load pointer at the instant of breaking indicates the breaking load. After the specimen breaks, bring the load control knob to the return position gradually and switch off the machine. Collect the 2 broken pieces of the specimen and fit them back together carefully so that their axes lie in a straight line. Note the distance between the punch marks near to the breaking point and also measure the neck diameter.
Tech now works, engineering the better way. Stress-strain curve is a stepping stone to understand properties of engineering materials. This curve is plotted for variety of engineering material during tensile test. In this video I will explain the stress and strain curve in very easy way. So, let's start with basic terms we have used in this curve, which are stress and strain. In tensile test, stress is calculated as load applied to a material, divided by the cross-sectional area of the material. The strain is the deformation or displacement of material due to applied load and can be calculated as change in length divided by original length. In stress-strain curve, the stress is shown along the y-axis, and strain is shown along the x-axis. As we load the testing object in tensile test, it begins to deform and stress continues to raise linearly up to a point A, on this graph. At this point A, if we remove the applied load on the testing object, it will restore to original shape without any deformation. As you can see in this graph, from point O to A, the stress and strain has a linear relationship, and stress is directly proportional to the strain within this region. Beyond point A, the proportionality between stress and strain no longer exists, hence the stress at point A is called the proportional limit. The Hooke's law is valid up to this point only. The slope of this line OA represents the Young's modulus, also known as modulus of elasticity, and it can be calculated as stress divided by strain within proportional limits. Higher slope means stiffer and stronger material, for example high carbon steel, and its curve will look like this. Whereas for flexible material like elastomers, curve will look like this. Remember, these curves are not to scale. With increase in stress beyond the proportional limit, strain being to increase more rapidly for each increment